this morning is the value of the molten salt reactor design in small modular reactor innovation. Note, SMR innovation is going mainstream, and I saw this on a sandwich board outside Starbucks in New York a couple of months ago, and Starbucks is inviting everyone to go and talk to their barista about molten salt reactors. So there we go. Our energy future is defined by a mountain. And that mountain is being created and is going to be is building in front of us and is going to be built over the next couple of decades for the next generation. And it's based on growing primary energy demand in non-OECD economies. This energy demand is being built by 6 billion people aspiring to have the middle-class lifestyle that we have in the West today. If the world economy is to supply that energy to meet that aspiration, we need an awful lot of clean energy. Now, providing that energy can't be done in the way that we received our energy as developed economies at that point in our development, simply because that is no longer acceptable. We need a different form of energy. This time, we need to supply energy that has three characteristics. It has to be secure. This means energy which is secure for the sovereign nation. So secure energy, economic energy, cost-competitive energy. Without cost-competitive energy, there's no economic growth. So it has to be economic energy and it has to be clean energy. This is called the TRILEMMA, and solving the TRILEMMA is probably the single biggest commercial, economic, investment problem that we face over the next couple of decades, certainly in my opinion. And the World Energy Council has got its own opinion on this. We must accept that we have to make hard choices in this generation to bring about real change for the future generation and the planet. Politicians and the industry must get real. So that's the World Energy Council's view on this problem. This is unique to the 21st century. It's probably unique to the last decade. This is a new pole star in the sky, which is driving energy innovation in every economy, across globally. Markets are emergent. They organize themselves to find solutions. There are many companies globally working on this problem. There are many individuals working on this problem, and they're organizing themselves in a way that private markets do to find solutions to this problem. That response is typically the response to market needs is never linear. What happens is you don't see much action until the critical threshold is reached, until the need is becoming appropriately urgent, and then you have a very fast, rapid response, and you have a new chapter in market dynamics. We have entered that new chapter today. We probably entered it about 10 years ago, and the evidence is all around us. This is not just a point about the nuclear sector. This is a point about energy innovation generally. So the evidence is the solar power, wind power, biofuel storage. These are all symptoms of this growing market need to solve the trilemma. And the nuclear industry is not immune at all to these market forces. We've entered a new chapter in energy innovation generally. But there's this realization, and this realization has probably dawned over the last 3 years. And that realization is that the current alternatives cannot alone solve the trilemma. Nuclear must play a role. That's a relatively recent view that I think many in the room would probably agree has been gaining traction probably only over the last 3 years. So what role can nuclear play? Nuclear is definitely secure. Nuclear is definitely clean. But nuclear possibly doesn't tick that box in terms of economic energy. If nuclear is to play a role in solving the trilemma, the important role that should be its inheritance, it must compete at the sharp end of commerce. And that means it must compete based on cost and convenience versus fossil fuel alternatives. To say it has to compete in its own industry as a technology which is incrementally better than the technology exists already, I think is missing the point. Nuclear must compete at the center of energy markets, and to compete, that's about competing with respect to cost and convenience. For only cost and convenience are the primary movers of corporate action. Where we stand today is that Gen 4 plus technologies have yet to demonstrate that they can deliver that important commercial touch point of cost and convenience, and we've been using this format for 60 years. So nuclear's economic problem requires fresh thinking. The small modular reactor is viewed as part of that new solution. So what commercial target does the small modular reactor have to hit? This is a chart, a rather simplified chart of, if you like, energy economics. So here we have the fossil fuel complex for power provision, which is broadly cheap to build, overnight capital cost. But once you built it, it's pretty expensive to operate and quite risky. Commodity prices drive this considerably. And then we have current nuclear, which is very expensive to build and comes in one size, enormous. But once you built it, you get you get the wonderful virtues of current nuclear, which is secure, reliable, dependable, safe baseload power. So the question for small modular reactor innovation is to occupy this area here. This area here is defined as an area which represents, on the capital side, a small modular reactor which is as cheap and convenient to build as fossil fuel alternatives. But once you built it, you have the wonderful operating cost virtues of nuclear: secure, safe, dependable, reliable baseload power. So that's the commercial target. The big question is, how do we get here? It's a $1 trillion question, and this is not a figure of speech. This is, in fact, a multi-trillion dollar question. There is an awful lot at stake in answering that question. And why is there a lot at stake? Well, global energy provision is probably 5% of gross world product, $3.5 trillion per year. That's probably at the low end as well. The equity value of energy companies today is $5 trillion, which is 7.6% of world equity market capitalization. And the enterprise value of those companies is even more. There is an awful lot at stake over the next couple of decades in this area here. So going back to the original question, how do we get a cost-competitive small modular reactor? There are two approaches. The first approach is to use Gen 3 plus economics with serial production, with modularity and the manufacturing of those modules in a factory setting. There are absolutely economies to be gained doing that. Or there's a second road to travel here. Or you use those economies of serial production and you take the rather difficult step, and that is you use a Gen 4 driven, Gen 4 technology where that technology drives cost innovation. So how do we get cost innovation in the small modular reactor space? Firstly, the first simple step is to make them small. You deal with the absolute issue of capex in the nuclear space, namely 10, possibly $15 billion project is very difficult to finance. It's very difficult to finance for a private sector company. That represents single axle risk on the balance sheets of a lot of the users, of a lot of the end customers of this technology. So to make it more convenient, more useful, make it small, $1 billion project is obviously easier to finance. That deals, make it small, you deal with the capex problem. How do you deal with the capex in terms of dollar per watt? Which is the relative economics of scale. Well, you can start off by employing the economics of serial production, modularity, manufacturing standardized components in a factory setting. And the third option you have is, I call it technology economics. Technology economics are such that it's the technology itself and the virtues of the technology, whatever type of Gen 4 technology one looks at, but it's the technology that drives cap and OPEX per unit. It's the technology that drives dollars per watt for instant overnight CapEx costs. So this is a picture of a Boeing factory in the background. So what you have here is modularity and a factory setting drives down cost per unit. But making it small, you have a competitive force that's pushing the levelized cost of electricity back up again. And the rule of thumb that seems to be emerging today when looking at the relative scale and influences of these two forces is that a small modular reactor at the top end of the range, 300 megawatt electrical, the savings you get from this piece here, economics of serial production, pretty much equal the lost economies you get from making it small. So you've got back to where you started. This is not getting us particularly close to that blue area, the center, the center of global energy markets. So we have to now consider technology economics. Technology economics is, I've summed it up in this thing that I refer to as the fundamental equation of nuclear power plant economics. The fundamental equation of nuclear power plant economics is the CapEx side is a function of the reactor system's inherent safety profile, for it is the inherent safety profile of your reactor system which drives cost to development, cost to license, cost to construct, cost to operate. And the inherent safety profile drives CapEx. So the question now becomes, we have a slightly different question, is what technology has the safety profile to offer cost innovation? What of the Gen 4 technologies has the safety profile, the inherent safety profile to drive cost innovation? When answering this question, I'm going to sort of offer a caveat, and that is, when attempting to answer this question, one has to be very careful and do not confuse the unfamiliar with the improbable. So looking at the inherent safety profile of the molten salt reactor, it's completely different. It's a liquid fuel reactor system, and as a result, the fuel is dissolved in the coolant salt. This leads to a completely different safety profile for the following reasons. Salts are fantastic coolants. They have high boiling points, and you have a reactor system that operates at atmospheric pressure instead of 160, which is typical for a light water reactor or a heavy water reactor. The absence of water, you don't have a source of explosive hydrogen. And fluids have properties that solids don't have. Fluids have a thermodynamic property of convective flow. This is very, very pertinent to your safety case with respect to decay heat management. You have something that all solid fuel reactor systems don't have. You have a fuel that's a liquid, and as a liquid, you can dissipate heat through a convective flow mechanism. So you have high passive safety is possible, and for these reasons, and that safety profile is not possible with solid fuel reactor systems. And as such, because of the fundamental equation of power plant economics, this leads to a completely different economic profile. You have a reactor system that is potentially smaller, simpler, and a far more manageable reactor system. So molten salt reactor technology employed in a small modular reactor format promises cost innovation in SMR design. The MSR route is the commercial road not taken. For the last 60 years we've been here. We've been commercializing the solid fuel reactor systems, of which there are many different types. This is the road that has been certainly traveled from a national lab perspective for a long time. But this is not the road that's been traveled from a commercial perspective. The reason this is pertinent today is that this road here, because market needs have changed, it's this road here that addresses market needs. This one doesn't. So an SMR-driven small modular reactor meets today's market needs. Now is the time to commercialize it. The US has a policy target of 80% of clean power by 2035. Currently it's 41% today. So there's an awful lot of clean power needed. US coal provision currently is pretty substantial as a result of coal-fired power stations being built in the 1970s. Most of those are relatively small, under 500 megawatt electrical. There's a very big replacement cycle associated with that coal capacity, and that replacement cycle is peaking in the next decade. So if you are to replace those coal-fired power stations need to be replaced, and that will result in another 130 gigawatt electrical power provision. And the question is, what's going to do that? A small modular reactor potentially could do that, certainly a very promising technology or commercial concept. And if it does do that, you would need to be building hundreds of small modular reactors over that product replacement decade, 2025 to 2035. You'd be building them at the rate of maybe 40 to 50 a year. If you could capture this market in an uncontested way with a small modular reactor, which is cost competitive with fossil fuel alternatives, you would have, this is a very, very sizable market opportunity. And this has to be put into a macro context. This is just one small part of a far larger global market for industrial heat and power. This goes back to the $1 trillion question, the $1 trillion opportunity. You've got an enormous market for a small modular reactor-driven SMR. You have the ability for the first time for nuclear to potentially co-locate close to point of demand. So you now have an energy source which is grid, pipeline, and water independent. This is particularly pertinent actually for emerging economies that don't currently have grid infrastructure. This would represent an energy technology which is highly strategic to many industries in many market verticals, and there's a list of them here. Obviously the traditional market for nuclear power provision, cogen on and off grid, in the mining sector, mineral resource extraction sector, in ammonia production, fertilizer production, hydrogen production, desalination. Water as a commodity is a big macro issue over the next couple of decades as well, actually. So the desalination industry is a growth industry, but that's going to be a very high energy user as well. You've also got the opportunity of having a cost-competitive, convenient energy source for remote communities and island states. In this case, you're competing with diesel generation off-grid. And because this is nuclear, and nuclear represents historically secure, reliable, dependable power, you have co-locating this type of SMR at a military installation is something that has a value proposition to not just the US military, but other countries. A once-through fuel cycle is the commercial standard today. France does a little bit of reprocessing, but I think it's fair to say that that's the commercial standard. A consequence of that is you have a fairly large amounts of unconsumed nuclear fuel, which is largely plutonium. And you obviously got your fission products. Today, unconsumed nuclear fuel, largely plutonium, is viewed as a liability. And so there's a commercial incentive to minimize that liability. The molten salt reactor consumes nuclear fuel far more efficiently. What you have is the opportunity of employing a technology that represents a step change in nuclear waste management. The first step, and this has to go chronologically, the first step is that molten salt reactors have the capacity to on their fuel cycle to give a far, far deeper burn. So you generate, at the end of the day, you'll be generating less plutonium waste per kilowatt hour with a once-through fuel cycle. This is obviously very relevant. In our particular reactor system, Terrestrial Energy's reactor system, we think we can generate about 1/6 less plutonium compared to a conventional reactor system. You also get, because you're operating at 700 degrees C, you get the obvious efficiencies of operating at a much higher temperature. You get much higher thermodynamic efficiencies and, as a result, less fission product waste on a per kilowatt basis. The second step is that fuel reprocessing, the second step is associated with the reprocessing of spent solid fuel. And this second step is for the future. There are substantial regulatory hurdles and policy issues to address here, but I just want to touch on the economics and the commercial potential. Molten salt fuel reprocessing or recycling has an entirely different set of economics. Solid fuel, if you want to process solid fuel, it's a complex 5-step process. And being complex, it's costly. You go from your solid fuel to your liquids, you separate your liquids through whatever chemical process is appropriate. You turn them back into solids, and then you have your probably one of the most expensive, difficult pieces is reassembling your solid fuel assemblies with MOX fuel, and this is a batch process, and you need to handle this stuff with a very long pair of tongs. So this is costly. Compare that to a liquid fuel, and I think our colleagues in the petrochemical industry would recognize the virtues of this process. You start with a liquid, you separate your liquid, you end up with a liquid, you miss out this expensive piece. This clearly has a very different set of commercial dynamics than this. And those commercial dynamics I'm suggesting today represent a possible second step change in the management of nuclear waste. So the question is spent nuclear fuel in the age of the trilemma a liability or an asset? Today it's viewed as a liability. But if you looked at this in terms of energy content that exists above ground, the US has vast amounts of energy sitting above ground. The value of that fissionable energy is about $2 trillion, priced at North American natural gas prices. The UK has a substantial amount of plutonium left over from the Cold War. The value of fissionable energy, and I'm using a reactor system, which is something which uses a fuel cycle to consume this fissionable material that is acceptable in a civilian context, so acceptable for the men in black suits. So the UK has 120 tons of plutonium left over from the Cold War. That would supply the UK for 21 years, total power provision for the UK for 21 years. And again, pricing those BTUs to European natural gas, you get to $500 billion. So the existing above ground stores of fissionable material should be viewed as national treasures, national energy treasures. But the $1 trillion question is, what technology can change this from a liability to an asset? And molten salt reactor technologies offer that opportunity because the liquid fuel form has an entirely different set of commercial dynamics when you're looking to reprocess liquid fuel. There's also an additional short-term advantage is spent fuel has to be processed in some way into forms for any waste disposal regime that we may choose in future. So you have some processed fuel in the near term. And molten salt reactors, liquid fuel, has substantial advantages in this processing. So my concluding remarks are, firstly, that we've got a new set of innovation drivers. We must, and it's called the TRILEMMA, and that is driving 21st century energy innovation for decades to come. You could view that as like a new pole star in the sky driving commercial innovation. The urgency of innovation is increasing. It's just every year it goes up and up. The market dynamic has changed, and there's a realization, probably quite recently, that nuclear must play a role. Nuclear can play an enormous role, for it solves many components of the trilemma: scalable, secure, clean, but nuclear must compete on cost and convenience at the center of global energy markets. It must compete with fossil fuels based on coal and natural gas. Economies of serial production and technology-driven cost innovation are both needed. This alone will not allow you to compete with these guys. So the $1 trillion question is what technology to use in an SMR to get cost innovation. The fundamental equation of nuclear power plant economics says that costs are a function of the inherent safety profile of your reactor system. A molten salt reactor has an inherently different safety profile. It is an inherently different reactor system at the most fundamental level. And only as a result, only a reactor system with an entirely different safety profile do you have the chance of sufficient cost innovation in the design and commercialization of a small modular reactor to compete at the center of the global energy industry. I just want to leave you with one thought, one final remark, and I borrowed that from Victor Hugo, who's a man who has cast a very, very long shadow over the last couple of centuries, and the thought is this: greater than the tread of mighty armies is an idea whose time has come. Now is the time to commercialize the molten salt reactor. Thank you very much.
Over billions of years, we have evolved immune systems because everything in nature lives in a chemical environment and in a radiological environment. 700,000 years ago, there was twice as much U-235, and so forth. So we have organisms that can survive in 1,000 times more radiation than a human can. Well, why is that? Cells have an ability to repair the broken bonds in DNA. They have the ability to perhaps repair some protein damage. They have the ability to digest the junk that's produced by damage, and they have the ability to actually eat themselves and kill themselves. So cells can actually die intentionally because they've become so screwed up inside because of various forms of chemical or radiological damage. And that's actually what happens when you have radiation poisoning, is you've killed cells, typically in the intestinal tract first, that are very susceptible and not able to handle that amount of radiation. So here's just a chart from Wikipedia about the metabolism in all our cells. It has exogenous damage from the outside world, radiation, chemistry, and so forth. It has endogenous damage from inside itself because it does metabolism. It burns its fuel internally for energy. And the most damaging things are oxidants, hydroxyl radicals, alcohol, those kind of chemicals that have a lot of oxygen available to corrode the insides of a cell. The reality is that over a few billion years, Mother Nature figured out how to deal with this. And so every cell, every second, every cell in our body does a repair of some sort. DNA repair in particular, in case of a break in a DNA strand. Natural radiation is in our bodies all the time because we eat. Potassium-40 is a low content of natural potassium, but it's radioactive and it's within our bodies. We have about 4,400 decays per second within our body of potassium-40. So our bodies are busy being radioactive. In 1946, Hermann Muller got a Nobel Prize for his work with radiation and other things on genetic mutations. And in his prize Nobel acceptance speech, he basically said that there's a linear relationship between radiation dose and the problems that it causes for the organism. But his data didn't actually support that. So this was an interview done with someone who knew about that from years later in the IEEE spectrum a little while ago. And basically his data didn't say that, and the people who worked for him disagreed with what he said in his Nobel acceptance speech. However, the problem was that the National Academy of Sciences took his words, and that's the beginning of where the standard for linear no threshold dose, in other words, no dose is too small not to cause trouble. And we know that that's not true from actual measurements. This is another example of a radiation lie from England. Christopher Busby was a doctor who said that there was leukemia in kids in Wales being caused by a nuclear reactor there. Well, it turned out he had fibbed. When they did the analysis of his data, he had done things like counting the incidence of leukemia twice. He had mixed up figures from small and rural areas, creating clusters of leukemia that didn't exist. And in fact, when they looked at the actual leukemia cases in one particular region, instead of having 10 cases, there was 1.